afternoon, everyone. My name is Robin. This is Brian, Brandon, and Sungwoo, and we're here to present our design and prototype of a modular all-terrain robot. Here's the agenda for today. I'm just going to give you a quick recap of where we're at as of spring break, including our budget and some of the design requirements. So our budget was $300. This did not include any shop materials, battery, the MyReal, or the driver. And the final deliverables are the shop drawings, 3D model, a functional prototype, as well as the final report. The main objectives for this was for our robot to have all-terrain capabilities and to also have the ability to climb stairs. As well as this, it had to appeal to the hobbyist market, including average and extreme hobbyists. In addition to this, one of the main requirements is it had to have a modular design so that the user can customize their robot based on their needs. So our initial design as a spring break, our frame consisted of square tubings that we planned on machining slots and holes to attach the other frame components. Also, to attach the other frame pieces, we needed to make T-connectors. Another issue with our design was we wanted to have our modular tracks, although we didn't have a final concept down. So at spring break, we had our tracks in one piece. Fortunately, they were not modular. Cyrus would have been too happy. So after much consideration, we came up with our new design. So first thing we did was decrease the overall size. This was to appeal to the hobbyists, so they weren't carrying around a huge robot. Also, the main change we did was we went from square tubing to extruded aluminum. This significantly reduced the amount of machining required because the extruded aluminum already has slots built in, and there are many accessories you can buy to attach to other frame pieces. Also, we implemented our modular track design. Because they're each single pieces that you can attach, the size can be easily adjusted, making it very modular. Sorry. Now I will pass it on to Sungwoo, and he will talk about our final.
Thanks, Robin. So as Robin mentioned, our final design of the robot has to have a very modular design. It's a very important thing when we were initially designing the robot. When we switched over to the T-slot extrusions, that literally made this robot infinitely adjustable. Using the anchor connectors, you can, as you can see here, you can slide the cross frame across wherever you want, tighten it down, you can move it back. The great thing is you can even do really minute changes like this. And it's this design, our robot is extremely versatile. Another main component of our robot design is the motor assembly. We mentioned last time we met, we're going to have a separate assembly that includes the motor, wheels, gears, and everything together. And we were actually able to create that. With this here, the users can attach the motors to any part of the robot they like. They can also add more motors for more power, allowing the users to create whatever configuration they want. It also allows the users to use this as a built-in tensioner, maintaining proper tension throughout the tracks at all times. Next is our modular tracks. Because our frame is so modular and able to turn into many configurations, we had to have tracks that can accommodate all those configurations. With the 3D printed design that we went with, you can increase and decrease the length of the tracks to whatever you need. And also its rigid structure allows the tracks to not flex as much, minimizing tensioning issues. And moving on, this is actually our convertible wheel design that we came up with after our last presentation. And this is actually the best wheels on the market right now. As you can see here, we have teeth on the wheels, allowing our tracks to sit on the wheel and gain traction. Very easily, you can go from that into an actual wheel design and then go back and forth. Unfortunately, I'm not qualified to discuss the technical specs of a very complicated design as this, so we actually have an expert that's going to take you through the design. I'm here to educate you on how to use our convertible wheel design. Here are the components you'll need. Our wheel converter, our wheel cover plate, our tracks, and a wrench. Step 1, remove the tracks. Step 2, slide on the wheel converter. Step 3, remove the nut and washer. Step 4, slide on the wheel cover. Step 5, replace the nut and washer. When secure the nut and washer, 17 foot-pounds of torque. There you have it. It's a one-matter wheel converter design. It's elegant, it's easy, and it's lightweight. Unlike So, with those 4 components that we mentioned, the frame, the motor assembly, the modular tracks, and the wheels, we can actually implement unlimited configurations to our robot. So if you want a stair climbing robot, we can do that for you. If you want a tank that won't stop at anything in its pathway, we can do that. If you want a really, really big robot, we can probably do that too. For whatever reason, you want your robot to look like a dinner tray, like some of the other competitors in the market currently, we can also do that. However, if you're not that hungry, you just want a little snack, we can do that as well. But creating a robot that's this modular in design and actually creating a prototype that works and functions as well as it does wasn't easy. And we definitely came across a couple problems along the way. I'll let Brian talk to you about some of the problems we came across and how we overcame them.
Alright, so one of the biggest problems that a lot of us faced was the machine availability. A lot of machines were down, like the water jet, we had to wait nearly 2 weeks just to get on that, and we just went across the street to the Gary building. And also, a lot of us were competing for the same machines, the CNC and the CNC lathe, so that really cut into the buffer time we left ourselves when we were manufacturing. The other thing was budget. We were given a $300 budget, and that really limited our possibilities, especially when we were quoted $200 just for wheel materials. And then another thing was the size of the robot. When we were designing on paper, we were thinking spanning 3 steps and maybe using 1.5 inch tubing. When we actually went to acquire that material, that was absolutely ridiculous. We were finding it was 30 pounds, just way too heavy. And then another thing that a lot of robots faced was the tread design. We didn't like rubber treads because it wasn't modular when we adjusted it. It was too expensive and it was too flexible. It would just roll right off, as you can see from last year's models. So we went on to 3D printing our own tracks, but that in itself also had their own problems. 3D printing tracks took a really long time. It took us over a week and a half, and even then that was at the lowest resolution. And because we printed at the lowest resolution, that was the downfall of our track. We had really weak tensile strength at the joints, and eventually we just had to drill holes and stick rods in glue as pins to work with the joints. And as of early this week, we found a new problem. We overspec the motor. So actually running it at nearly 20% speed caused the twisting of the frame because the only thing holding together was just dropping the spring. So as of this point, we actually added a couple of gusset plates to help create it, make it more rigid so it will not flex as much. And we'll see how that goes. Now Brandon will take you through what we've learned through this process.
Thanks, Brian. So what did we learn? We learned multiple manufacturing techniques using the lathe, milling machine, water jet cutter, and 3D printer. We were able to build everything we see here today. We learned valuable time management skills. We were able to set aside extra time each week to focus on specific parts of our robot design. We also had, the buffer time was also really great because we did run into multiple problems. We learned how to simplify during our design process. Initially, as Brian said, we were going to use 1.5 inch square tubing, which is actually 4 times as big as what you see here right now. So it would add more than double the weight. And when we went to the shop, we realized we could scale down. Another thing was visualizing scale. Oh, sorry, I got something mixed up. So it's simplified the design process. We switched from aluminum square tubing to extrusion, which allowed us to actually cut down our manufacturing time. For visualizing a scale, we were able to put in CAD, we made a model of the stairs, so every time we came up with a new iteration of our robot, we can compare it easily. And for tolerancing, we were able to use tolerances to get our bearings to press fit into our pillow blocks very well, as well as a nice tight fit between our shaft and our wheels. So, what can we do now? So what we want to do is mix better treads, maybe improve on the design, make a better pillar system, possibly if we print in high resolution, and look at different materials. We want to improve our motor block, possibly adding a case around it to both hold it more sturdy to the frame as well as cover our gears. We want to possibly improve our sensor code we're going to improve our sensor code to calibrate it for our competition we have next week, as well as in the future, we could possibly add longer range sensors or computer vision for collision detection to move from a semi-autonomous robot to a fully autonomous robot. And overall, we can improve the aesthetics, possibly paint our robot, fix our wiring, just make it, and adding a cover plate to try to protect all the components and make it look a bit nicer. Now someone's going to finish this off with
As you all know, or should know, we have a website, and we update it very regularly. We have an Instagram page as well. A lot of you guys may be finished with your projects, but we still have a competition coming up next Wednesday with the other three groups as well. And we are still tackling some of the issues, last minute things, in order to optimize the robot as best we can. So please check out our website and keep up to date with kind of how we're finishing up here. And I think having said that, with four really bright individuals like this, it's not enough to create a robot like this. This is just too high-tech. I want to thank Cyrus for really pushing our limits in terms of design and really pushing modularity. And we did it. Charlie, thank you for really encouraging us all the time. Every Monday and Wednesday morning, we come in depressed and we leave encouraged, ready to take on a new challenge. And Dave, Steven, Greg, and Brian, really, the time in the shop would not have been as effective without them. Ernie and Danilo over at the Carry building were amazing in helping us get some stuff done last minute. And I think that's everything we have. Any questions? John?
So you guys left off, you had board gear designs where you're adding gears into the wheels.
Earlier, yeah.
You've gone to better gears. Is that probably as far as manufacturing goes or just sourcing those?
For worm gear, we realized we didn't actually need the gear ratios for the torque. The motors are actually well within the specs, so we just chose the double gear for the orientation to make it. And the deflection. There's some deflection problems with having the worm gear at an angle with the spare gear. So the double gear kind of helped with that, for sure.
Dan, I think.
What's the meaning of this triangle we have here?
Oh, I guess I gotta clear that up. I just want to say, yeah, we, as you guys know, we are 4 groups competing in a stair climbing competition. And although we are competing next week, honestly, throughout this whole process, as soon as the first presentation was over, we were actually really helpful with each other, supporting each other, and coding, manufacturing, little design critiques here and there. And I just wanted to show that, yeah, it is. Although we're competing, we're a good group of friends, and it's all in good fun. Unfortunately, I wasn't able to get a picture of all the robots together because they were all assembled and disassembled at different times. So I did as closely as I could sketch 4 robots. So that would be one group, that's the other group, that's the other group, and that's ours right there. So I just wanted to put it all together to show that we are, all in unity here. Good question, Dan. Kurt?
Yeah, go back to the gears. You guys mounted right
questions. Do you have a suggested solution, maybe cover it up so things don't get lodged in there or gears get damaged?
Oh yeah, as I said earlier, we're thinking of designing a case to protect all of the gears, as well as just for the motor assembly, basically, just to protect it from outside environments.
I'll do it for and then use it. Like,
I think you should just consider a plastic frame to retract it.
plastic is very rigid, will not break.
How are the motors mounted to the frame? Is it just pipe clamps?
Okay, so we have a motor support design in there that's actually it's cupping the motor itself. So it's not literally just a motor against a flat wall. We have the cup shape and then the two pipe clamps. Having said that, like I said earlier, we are having some issues with the motor still moving a little bit. So we will probably find a slightly better way to increase the strength of the clamps.
Ken or Cyrus, do you have any questions? That's it for questions. Thank you.